Docker plays a crucial role in the field of artificial intelligence, effectively addressing diverse challenges inherent in AI development and deployment. A key challenge in AI is the efficient management of dependencies, libraries, and runtime environments, especially when collaborating with diverse teams or deploying models across various platforms. By encapsulating AI models with specific runtime environments, libraries, and dependencies into Docker containers, developers can overcome the "it works on my machine" problem, ensuring consistent performance across systems supporting Docker. Additionally, Docker seamlessly integrates into continuous integration and continuous deployment (CI/CD) pipelines. The containerization provided by Docker ensures that each AI application operates within its isolated environment, preventing conflicts and optimizing resource utilization. Whether you're a data scientist, machine learning engineer, or AI developer, incorporating Docker into your workflow has the potential to significantly enhance the efficiency and reliability of AI projects. Docker is an open platform for developing, shipping, and running applications. It provides the ability to package and run an application in an isolated environment called a container. Users can run many containers simultaneously on a given host. Docker uses a client-server architecture that consists of several components working together to manage containers. The server part is a Docker daemon, also known as the Docker engine. It is a background service responsible for building, running, and managing Docker containers. It listens for Docker API requests and manages container processes. The client part is a command line tool or user interface, also known as the Docker client, used to interact with the Docker daemon. When you use Docker, you are creating and using images, containers, networks, volumes, plugins, and other objects. Docker images serve as the template for creating Docker containers, which are running processes of these images. A Docker registry is a cloud-based registry service where developers can store, share, and discover Docker images. For example, when we use Docker pull command, Docker pulls the required image to local system from the configured Docker registry. Let's delve a bit further into the Docker platform with an example before getting into its specifics. The Docker run command demonstrated here is utilized to instantiate an Ubuntu container, offering an interactive terminal session for users to execute commands within the newly created container application. Behind the scenes, Docker fetches the Ubuntu image from your configured registry and initiates a new running process with a private read-write file system. Subsequently, Docker establishes a network interface, connecting the container to the default network and assigning an IP address to it. This allows the container application to connect to external networks using the host machine's network connection. Once the container starts and the bash shell is running, users can execute any desired command within the newly created container. Upon using the exit command to conclude the bash shell session, the container stops but remains preserved. You can restart or remove it later as needed. Docker Engine, often simply referred to as Docker, is a fundamental component of the Docker platform. It utilizes a client-server architecture, where the client and daemon can either run on the same system or communicate over a network. The Docker daemon, also known as the Docker engine, is a persistent background process responsible for managing Docker containers on a host system. It oversees tasks such as building, running, and monitoring containerized applications. The Docker client, available as a command line tool or user interface, enables users to interact with the Docker daemon. Docker Engine exposes a REST API facilitating communication between the Docker daemon and the Docker client. This API defines a set of commands that the client employs to interact with the daemon. Overall, Docker Engine plays a central role in the containerization process, delivering essential services and functionalities necessary for creating, deploying, and efficiently managing Docker containers. Docker images are immutable templates that include the application, runtime, libraries, and dependencies required for running an application. These images are constructed using a set of instructions specified in a text file known as a Docker file. The Docker file consists of a sequence of commands and parameters that define the steps for creating an image. It outlines the build process, encompassing the selection of a base image, addition of dependencies, and configuration of the runtime environment. Docker employs a layered file system, where each Docker file instruction contributes to a new layer. The provided Docker file example illustrates the creation of an Alpine Linux image. It uses Alpine Linux version 3.14 as the base image and installs the curl package onto it. To build an image, navigate to the directory containing the Docker file in a terminal and execute the docker build command. Docker images are constructed using a set of instructions given in a file called a Docker file. Begin by creating a text file named Dockerfile in the root of your application or project, which will contain the instructions for building the Docker image. Specify the base image for your application, typically representing a starting point with a base operating system. In this example, the base image is Ubuntu 20.04 obtained from Docker Hub. Use workdir instruction to set the working directory within the container where subsequent commands will be executed. The copy instruction will transfer application files from the host machine to the image. Use the relevant package manager to install dependencies required for your application. In this example, apt-get is used to install Python 3. Employ either the cmd or entry point instruction to specify the default command executed when a container is run from the image. Once the Docker file is created, execute the docker build command. This command constructs an image named myapp with the tag 1.0 from the Docker file in the current directory. Once the image is built, you can push it to a container registry such as Docker Hub. Docker containers provide isolation, portability, and consistency, enabling you to package and run applications in a reproducible manner across various environments. The following example illustrates how to run an Nginx web server in a Docker container, making it accessible on your local machine. Start by pulling the Nginx image from Docker Hub using the following command. Then, run an Nginx container in detached mode in the background, mapping port 8080 on your host to the default Nginx port 80 in the container. Open a web browser and navigate to localhost 8080 to view the default Nginx welcome page. To view a list of running containers, including the one you just created, use the docker ps command. If you want to see all containers, including stopped ones, add the -a option. To stop a running container, use docker stop, followed by the container ID or name. You can remove a stopped container with the docker rme command. It's essential to note that each time you run a container, it's a new instance, and any changes made to the file system are specific to that instance. Docker Hub is a cloud-based registry service provided by Docker that allows users to store and share Docker images. It serves as a central repository for Docker images, making it easy for developers to access and distribute containerized applications. Docker Hub also provides version control for images and simplifies the process of sharing, distributing, and collaborating on Docker images, fostering a vibrant ecosystem around containerized applications. Users can search for Docker images using the docker search command, facilitating the discovery of existing images. Docker Hub enables users to pull pre-built images from the repository to their local environment using the docker pull command. Similarly, developers can push their custom-built Docker images to Docker Hub using the docker push command. To utilize these features, users need to create a Docker Hub account, and the docker login command facilitates authentication. Docker Hub supports both public and private repositories, accommodating various use cases, from open-source projects to proprietary applications. Docker Compose is a tool that allows you to define and manage multi-container Docker applications. It enables you to describe your application's services, networks, and volumes in a single file, typically named Docker Compose.yml. With this configuration file, you can define the relationships between containers, making it easier to deploy and manage complex applications. Each containerized component of the application is defined as a service, representing entities such as application servers, databases, or any other containerized unit. Docker Compose automatically creates a default network, facilitating communication between containers. Additionally, you can define volumes in the Docker Compose file to persist data across container restarts or share data between containers. Now let's explore an example to understand how Docker Compose works. Let us consider a simple example of a web application with a front-end and a back-end service. This Docker Compose file defines two services, web and back-end. The web service utilizes the latest Nginx image and maps port 8080 on the host to port 80 on the container. The volume key mounts the web data directory on the host to the specified directory inside the container. The back-end service employs the latest Redis image. Once the services are defined, use the Docker Compose Up command, which reads the dockercompose.ml file and starts the defined services. Similarly, the Docker Compose Down command stops and removes the containers defined in the dockercompose.ml file. Docker Compose greatly simplifies the deployment and management of multi-container applications, providing a convenient way to define, orchestrate, and scale containerized services. Before we wrap up, let me emphasize the immense value of hands-on experience in mastering Docker. The concepts we have covered today are foundational, and the real magic happens when you put them into practice. Docker is a tool that rewards exploration, experimentation, and creativity. We encourage each one of you to embark on a practical journey with Docker. Start by creating a simple containerized application, play around with Docker Compose, and witness firsthand how it streamlines the deployment process. If you have any questions or need further guidance, feel free to reach out to the course instructor. They are there to support you and provide comprehensive instructions on how to approach the practical exercises effectively.